Everybody, it's video notes 4.3, and we're going to talk about one other kind of bonding, metallic, and then look at the structure and function for all kinds of bonding. So please read section 5.6 and pages 441 and 442. So metals, we looked at metals when we first were looking at the periodic table. We saw some of their properties. So metals are held together with variable bond strength. So they have variable melting and boiling points, although they're usually higher than some covalent things. They're good conductors of heat and electricity, and they're malleable. That means you can make them into shapes, and they have high metallic luster. So what model can we use to explain metallic bonding properties? So metal atoms bonded to other metal atoms are not considered compounds. The bonding occurs through, again, non-directional covalent bonds. Now, I say non-directional because when we talk about covalent bonds, we talk about atoms sharing electrons, and they're always set in between the two atoms that are sharing them. Okay. This is not what's going on in metals. In metals, all of the metal nuclei line up, and then their valence electrons are shared in all directions with all the other metal cations. So that's what I mean by sea of electron in non-directional bonding. So what are some properties of metals again? Well, those properties are that metals are malleable. So if you hit a metal with a hammer, instead of being brittle and breaking, it'll bend into different shapes because the metal cations are lined up, and the sea of valence electrons shifts into different shapes. Also, you can see that electricity can flow and heat can flow through metals because those valence electrons that are shared by everybody in that sea of electrons are delocalized and can move throughout to carry heat. They can also carry electric currents. Right? So, metal properties can be described by their bonding pattern. So let's look at ionic bonding again and compare it to metallic bonding. So ionic bonding creates brittle solid crystals, whereas metallic bonding creates shiny malleable solids. Except for mercury. Mercury is a liquid, but all other metals are solids. Okay? Ionic bonding, repeating pattern of positive and negative ions. Metallic bonding, atoms turn into cations with their mobile outer electrons that can move throughout sea of electrons. Ionic compounds do not conduct electricity as solid. Metallic substances do conduct electricity. Many ionic compounds dissolve in water. Metallic substances do not dissolve in water, although some react with water. Okay, and then ionic compounds do conduct when they dissolve. Electrons. Electrons in ionic compounds get transferred from the cation to the anion, metal to nonmetal, or the positive ion loses and the negative ion gains. Electrons in a metallic substance get shared in all directions, so non-directional because it's shared in all directions, not just one, and they bond by all the to help hold all of the metal cations here. Okay, now we got to put it together with covalent. Right, so here's the comparison of all the three kinds of bonding that help us explain different properties of different substances. So metallic bonding, metals are two or more metals were the same metal. So silver is held together by metallic bonds. Zinc is held together by metallic bonds. Copper is, we could go on forever. Covalent bonding, there's two nonmetals held together by covalent bonds. Okay. Metallic bonding, the sea of electrons. Covalent bonding shared and stuck between atoms are electrons. Okay, so electrons, electrons, electrons. Notice valence of electrons is the key to bonding. Okay, how is that different than ionic? You got a metal and a nonmetal, and the valence electrons are transferred from the cation to the anion. Okay, so conductivity. Metallic substances conduct as solid and liquid. Covalent substances never conduct, and ionic substances conduct as liquid or aqueous, but not as solid. They have variable melting points. Covalent are variable, but they're the only ones that have low melting points. And ionic compounds usually have the highest melting points. Okay, insoluble in water are metals. Polar are soluble in water for covalent substances. And ionic compounds, many are soluble in water. And finally, variable bond strength for metallic, high bond strength for covalent, but then low intermolecular forces. Ionic compounds are high bond strength. Okay, so here again are the models for bonding, but in visual form. So here's ionic. Notice you have the cations and your anions. making crystal lattices to make the solid little crystals. Metallic substances, the sea of valence electrons between all of the metal cause these shiny, malleable substances. Okay, and covalence, I have a couple of examples. Sugars held together by covalent bonds, water, carbon dioxide, sulfur hexafluoride, shared electrons all over the place. Shared electrons make molecules, and that's how those form. Okay. All right. So don't forget your 7 diatomic elements. They're going to come back for you. Okay. Remember North. So these are elements that always pair up if they're alone. They're held together by covalent bonds, and they make tiny diatomic molecules. So remember super 7. And it points to hydrogen. North. Okay. So now we can talk about chemical structure overall. So the structure of a substance determines its properties. Ionic substances like sodium chloride. We talked about covalent substances and metallic. Now covalent, we talked about covalent molecular. We have the small molecules. Look at all those ones that we kind of talked about. And then the big molecules, polymers, proteins, DNA. This is the one we haven't really talked about, or covalent networks. So we're going to talk about that a little bit. But that's how electrons are shared to make diamond and quartz and that kind of stuff. So let's talk about polymers. Polymers, we did some labs with them. You saw the differences between them. But the long chains of covalently bonded substances can fold over on each other to make them rigid or flexible at with different properties. Okay? So for instance, slime, we have glue, right, glue, and then we added the borax. And then look, it made hydrogen bonds to give it stronger properties than glue alone. But all of these pairs of electrons being shared are covalent bonds. Right, so you got your properties. So what are polymers? Polymers start with a monomer, like ethene or chloroethene, and then they polymerize because these pairs of electrons can be used to make more bonds, and you get repeating patterns, so you get the polymer. Okay. Same with this monomer, polymer. Okay, so polymers can be flexible, they can be rigid, they can be fire resistant, all because of how their long chains fold on each other, how they hydrogen bond between chains, how they covalent bond within. Okay. Ionic compounds, based on their structure, have these properties, and we looked at it. They're brittle when you hit them, okay, so the crystals crack. Their ions are fixed and they can't move when they're solid, so there's no current can run through when they're solid. But then when they're molten or aqueous, then the ions can move and conduct electricity. All right, network covalence. That's a new one that we haven't talked about yet. But many network covalence substances are rigid and high melting points. So here's carbon. These are all carbon atoms. And what those carbon atoms do is share electrons with each other in all 4 directions. And then those electrons are stuck in place because they're being shared in between atoms. And so you get this network of covalently bonded carbon atoms to make diamond. Right? And so it's really rigid and strong. In order to melt diamond, you have to break a covalent bond. So it's going to take a lot of energy. Okay. Now, here's sand. You see you have covalent bonds here and here and here. And so you get this rigid structure. Now, when glass forms, it's sand at high temperatures, and then it makes this amorphous solid. Okay. But still, all of these covalent bonds make a strong network. Okay. Now, here's some other network covalent solids. Graphite, right? So we got a covalent bond between carbon atoms. Right? Covalent bond. So you got these carbon atoms that make rings, right? Covalent bonds, says right there. Okay. Now, van der Waals, also known as London dispersion forces, okay, are holding these sheets of covalent bonded carbon atoms together. And so then this sheet of covalently bonded carbon atoms can come off, rub off onto paper. Yay, we get to write with a pencil. Woo! Okay, so here's graphite. Now, graphite is covalently bonded, and it makes a network, but then sheets, like the van der Waals forces holding those sheets of covalently bonded atoms together, can rub off, and so this is weak, and then this is strong. Okay? Alright, so let's look at what you need to do to review. Read through this, write it down, make sure you memorize your ions. So through it in your friends. For instance, NH4 is ammonium. Because understanding ionic compounds means you have to recognize the polyatomic ions and how they come together, and other ions as well. Okay, so you have metallic, covalent, ionic. Now, how can you tell what type of bond is present? You need to know the types of properties. You need to know electronegativity, and you need to know the atoms involved. So this is it metals? Is it nonmetals? And then, if you decide what kind of bonding is present, make sure you have evidence to back up your choice. All right, read those sections, do this stuff, and we are through. Peace out.